Assalamu alaikum. Hi everyone. This is actually the continuation of the previous video lesson, and in this video I would like to explain one concept in a counter system which is called the self-starting counter. This self-starting consideration normally occurs when there are some unused states that were not included in the counting sequence, of course, and the flip-flops are non-resettable such that the user cannot force the counter to count beginning at a specific initial state. So we get to the definition of the self-starting counter. That is a counter that has the ability of entering the proper sequence or the correct sequence no matter how the counter starts up. Which means, suppose that this is the counting sequence of your counter, A, B, C, D, E, and repeat, in which you have 5 used states, which is obviously A, B, C, D, and E, and 3 unused states, which are F, G, and H. Imagine that you just power up your counter circuits and the flip-flop produce a random state based on the initial condition of the circuit. And since the reset button is not available, you just let the counter count from that random initial states. So that random initial states can be either A or B or C or D or E, or even one of the unused states, F or G or H. If the initial state is one of the used states, you don't have to worry because the system already enters the correct counting sequence. For example, if the initial state is state C, and then it will go through the correct sequence, C, D, E, A, B, C, D, E, and so on. But what if the initial state is one of the unused states? So how to ensure that it is eventually will transition to the used state and enter the normal sequence or the correct sequence? So the answer is, this can be done by doing a so-called the reverse engineering technique. For that purpose, I repost the same problem from the previous video, namely the counter with irregular sequence. And let's see how to identify whether this particular counter is self-starting or not. So here is the state diagram, the state transition table, the Boolean expression, and so this Boolean expression that were derived from the K-maps, and the circuit diagram that was built based on the Boolean expression. So here our task is to investigate what will happen to the counting sequence if the initial state is one of the unused states. That is state 1, state 4, and state 7. So now we bring our focus on the state transition table. Okay. Here are 3 rows, 1, 2, and 3, that are filled with don't cares, as can be seen here. All are don't cares. All right. So these don't cares corresponds to the unused states 1, 4, and 7. Okay, so these Boolean expressions are the inputs of the flip-flop, of the D flip-flops that corresponds to this. So all these expression corresponds to this column. So each K-map filled with 3 don't cares, such that, as can be seen here, the yellow don't care, this, and this corresponds to the state 1. So the blue don't cares, this corresponds to state 4. And the green don't cares, this one, this, and this corresponds to the state 7. All of them, remember that all of them are the unused states. Let me clear the scribble first. Okay, so we know that don't cares can be either 0 or 1. If a don't care is included in a group of the K-map, so it is treated as number 1. And if a don't care is left out from the group, it is treated as 0, which means this yellow don't care acts like 1 and 0. This is 0 because it is left out from the group. Then this blue don't care acts like 0, 1, and 0. And finally, the green don't care acts like number 1, 0, 0. So using these values, we can update the flip-flop column of the state transition table to become, so now we update it. So that yellow don't care now becomes 1, 1, 0. Sorry, 1, 1, 0. The blue don't cares becomes 0, 1, 0. And the green don't care becomes 1, 0, 0. So our aim is to define the next states of the unused states. So these updated values can be transferred to the next state column, because this is the D flip-flop, and the D flip-flop input is equals to the next states. So we just copy all of them, all of the updated values. So this is this. Sorry. And okay, so now we have updated our next state column. So notice that we don't really bother about the output column because it does not influence in determining the next states of the unused states. Okay, now we can now update the state diagram by including the transition of the unused states. So from the updated state transition table, we can see that 1 goes to 6. So 1 goes to 6. 4 goes to 2. Goes to 2. And 7 goes to 4. So we can already conclude that this particular counter is a self-starting counter because it has the ability to enter the correct sequence even though it starts at one of the unused states. Even though it starts at the one of the unused states, it has the ability to enter the correct sequence. For example, if it starts with number 1, then it will go to number 6 and then circulates in the correct sequence. If it starts with 7, number 7, the path will be a little bit longer because it will go to 4 first, but eventually it will enter the correct sequence through number 2. Okay, and lastly, how to tell that a counter is non-self-starting? Okay, so if the unused states only circulates among themselves and never goes to the one of the use states, then we can say the counter is non-self-starting. For example, by any chance, by using after doing the reverse engineering procedure, so if we figure out that, for example, 1 goes to 4, for example, 4 goes to 7, and 7 goes back to 1, and then repeats among themselves. So in this case, the counter is non-self-starting, which require a reset to force it to start at one of the use states. Okay, so before I end this video lesson, let me repeat what is the definition of self-starting. It is a counter that has the ability of entering the proper sequence no matter how the counter starts out. Alright, so that's all for now. Thanks for watching.